For years, we've been completely fascinated by, the relentless march of technology, especially in AI. We've chased bigger chips, faster processors, these massive data centers. But what if the real revolution, the actual engine driving AI's incredible progress, isn't just about faster silicon? What if it's really happening inside the machine, in the code, the algorithms themselves? Today, we're going to crack open a principle that really reshapes how we understand AI advancement: Williams' Law. This deep dive is going to reveal the frankly startling truth about how software ingenuity, not just brute force compute, is quietly unleashing exponential power. It fundamentally changes everything you might think you know about AI's future. We'll explore the core idea, dive into the fascinating conceptual math behind it, figure out how we can actually measure its impact, and finally, what it all means. For everything from the AI on your smartphone right up to the global landscape of AI research, get ready for some, well, pretty profound insights, because this really does shift the perspective on what drives artificial intelligence. Okay, let's really get into this then. For a long time, our understanding of tech progress has been, well, heavily influenced by hardware-centric ideas. Think about Moore's Law, for instance. That observation that, the number of transistors on a chip would double roughly every 2 years, that set an expectation, right? An exponential increase in raw computing power. And more recently in AI, we've heard about Huang's Law, suggesting an even faster pace for specialized AI hardware like GPUs.
Exactly. Those GPUs that power so much of today's AI.
So these laws kind of led people to believe you could just, wait for faster chips and your AI would naturally improve. Just throw more hardware at the problem and progress follows. But what if that's just not the whole story? What if the path of thinking smarter in the software and the algorithms is actually accelerating faster than simply working harder on the hardware side?
That's precisely the pivot point, isn't it? While hardware scaling absolutely provides an essential foundation. It lets us build bigger models, handle more data. It typically offers what we call linear gains for a fixed algorithm.
Sure.
If you double your processing power for a specific task in a specific bit of code, you generally, well, double your throughput, maybe a bit less sometimes.
Right. It's a direct proportional thing. More power in, roughly proportional speed out.
Exactly. Williams' Law, however, brings into sharp focus that algorithmic innovation, whether it's a breakthrough in model architecture, a smarter way to train, a more efficient data strategy, this can yield compounding exponential benefits. This fundamental distinction is absolutely vital. It's crucial for understanding where the real leverage, the sustained progress in AI, now truly resides, especially, as hardware improvements start hitting those physical walls, those economic constraints. It's a fundamental reevaluation of the power dynamics.
Okay, so let's get right to the core of Williams' Law then. It's this principle that basically formalizes the whole think smarter, not harder idea for AI. It suggests that cumulative improvements in software innovations, in code, model design, math approaches lead to exponentially growing performance gains, even if the hardware stays the same, fixed hardware.
Right. And conversely.
Conversely, if you only scale up the hardware but keep the algorithms exactly the same, you're looking at, well, best case, linear gains.
At best, yeah.
This is a massive difference in growth potential, isn't it?
It really is.
Yeah. Imagine, like, two ways to make a factory produce more. One way is just build a bigger factory, more machines. That gives you steady, proportional increases, right?
Yeah.
Linear gains. The other way is to completely re-engineer the manufacturing process itself, make every step way more efficient, and those efficiencies build on each other, they multiply the output. Williams's law tells us that that second path, the ingenuity path, offers those multiplying returns.
And to put that in context, as you mentioned, Moore's Law was primarily about that exponential growth in raw compute power. Over time, more transistors packed closer together. Huang's Law, similarly, noted rapid improvements in specialized AI hardware, often through better architectures, more parallelism. Both describe an amazing exponential growth in hardware capability over the decades, no question.
Yeah.
But here's the crucial nuance. For any specific fixed algorithm running right now, doubling the hardware capacity generally translates to, at most, doubling its performance.
Right, just runs twice as fast.
Yeah, it's a linear improvement for that instant. Williams's law introduces this completely different compounding dynamic. The algorithm itself becomes intrinsically more efficient, more capable. It achieves far more with the same raw hardware. It's like the difference between breeding a faster horse versus inventing the car. Fundamentally different kinds of progress.
And this is where it gets incredibly relevant for us right now, because hardware improvements are starting to bump up against some serious physical limits, aren't they?
They are. We're talking atomic scale, quantum effects, heat dissipation. It's getting harder and more expensive to maintain that old pace.
So as that pace inevitably slows down, Williams's law suggests something really hopeful. AI progress doesn't have to slow down with it. We can potentially sustain, maybe even accelerate that exponential growth by shifting focus, by investing in algorithmic innovation.
Hey, exactly. It's about changing how computation is performed, how decisions are made, how data is processed, not just relying on throwing more brute force resources at the problem.
It means we can still look forward to a future of continuous innovation, even if the silicon isn't always doubling in speed quite as quickly.
Absolutely. It shifts the bottleneck from physics to ingenuity, in a way.
Okay, so how do we move beyond just the concept? How do we actually quantify this? You mentioned performance depending on hardware and algorithms.
Right. To make Williams' law quantitative, we can think about AI performance, let's call it P, as a function of two main things. There's the hardware capacity, let's call it H. That includes things like raw speed, FLOPs, memory bandwidth, number of cores, the physical stuff. And then there's a measure of algorithmic innovation, which we call the A index. This isn't just a vague idea. It's a structured way to model how these two drivers interact and contribute to the overall capability and efficiency of an AI system.
Okay, P depends on H and A, hardware and algorithm.
PHA. It gives us a framework to mathematically separate the influence of pure hardware power from the ingenuity baked into the software.
Okay, like your cake analogy from earlier, P is the deliciousness of the cake. HH is the kitchen equipment oven size, mixer power, storage space. More equipment helps, but you hit diminishing returns, right? You can only bake so fast, even with a giant oven.
Exactly. That's the hardware part, HH to the power of Ohm.
Yeah.
That alpha exponent is usually around 1, meaning roughly linear returns, or sometimes even less than 1, signifying diminishing returns.
So doubling the hardware might not quite double performance because of other limits, like parallelization issues or memory bottlenecks.
Precisely. Hardware gives a steady push, but often faces constraints. Roughly proportional returns, sometimes less.
But then comes the secret ingredient, the A index, the algorithmic magic.
This is the game changer.
This is discovering a whole new baking technique, maybe a fermentation process, that makes every cake exponentially better or faster to make without needing a bigger oven.
That's the expli term in the equation. The expli means exponential. Lambda is a constant determining how strongly each unit of A, our algorithmic innovation index, boosts performance. And because A is up there in the exponent, even small increases in A, small improvements in algorithmic smarts, can lead to massive exponential gains in P.
Ah, okay, so that's what formalizes the idea. Software is exponential, hardware is linear. The math actually shows it.
Exactly. That exponential term is where the compounding power of algorithms comes into play.
So what is this A index exactly? How does it grow?
Good question. The A index itself is essentially a cumulative measure of algorithmic improvement. Think of it like a running score, constantly growing, tallying up all the clever ideas, optimizations, and fundamental breakthroughs integrated into AI over time. Every significant algorithmic idea, a new model architecture like the transformer, a better training method like atom optimization, smarter data strategies each contributes to A.
So it accumulates.
It accumulates, exactly. It's like compound interest for intellectual capital. Each new insight builds upon and potentially multiplies the impact of all the previous ones. And while A isn't something physical you can, hold in your hand, it represents the cumulative difficulty removed from a problem, or the capability gained through sheer algorithmic ingenuity. Over decades, as dozens, hundreds of these innovations pile up, A grows. And that exploit term can become huge, explaining those massive historical AI performance gains that hardware alone just can't account for.
Can we make it more tangible? Like, what does 1 unit of A mean?
We can try to calibrate it. For instance, we could define a unit increase in A1 as corresponding to, say, a 10% reduction in the compute needed for a certain accuracy, or maybe a 10% accuracy boost for fixed compute. The exact units aren't as crucial as the principle. Consistent incremental improvements compound exponentially.
Okay, that makes sense. So with this mathematical foundation, PHA, PH00, say, we can define some powerful new metrics, right? You mentioned Williams' gain.
Yes, Williams gain, or WG. This metric quantifies the multiplicative performance boost you get just from an algorithmic innovation, keeping the hardware H completely fixed. Think of it as asking, how many times better did my AI get simply because I implemented a smarter approach without touching the hardware?
Like finding a tune-up for your car engine that doubles its power without changing any parts.
Exactly like that. If an innovation moves the index from A to A plus A, the Williams gain G is simply gay. So Williams' gain of G2 means that algorithmic idea double the performance on the exact same hardware. That's profound.
Doubling performance. That could take, what, 2 years, maybe more, according to Moore's law for hardware?
At least, sometimes longer, especially now. Williams' gain highlights the immediate, sometimes dramatic impact of just being smarter in the software.
And you mentioned a real-world example, chain of draft.
Right, a fantastic example. This recent prompting innovation for large language models, chain of draft, it achieved a Williams gain of roughly 13.
13 times.
13 times improvement in efficiency or speed, depending on how you measure it, just from a software tweak in how you prompt the model. No new GPUs needed.
Wow. That's incredible.
And the truly amazing part is the compounding. If you have 3 separate innovations, maybe each gives a modest 1.5x boost on its own.
They multiply, right? Not just add up.
Exactly, they multiply. So 3 1.5x boosts combined to 1.5 times 1.5 times 1.5, which is about a 3.4x overall gain. That multiplicative compounding is the revolutionary core of Williams' law.
Okay. And there was another concept, elasticity, like from economics.
Yes, the elasticity of performance with respect to innovation. It basically asks, how responsive is performance, PP, to a small change in our algorithmic innovation index, A? Formerly, it's EPA, AP. Under our exponential model, this simplifies nicely to just EA.
Lambda times A. Okay, so what does that mean practically?
It means the elasticity, the responsiveness, grows linearly with A. When you're just starting out, when A is small, a 10% improvement in your algorithmic innovation gives you roughly a 10% boost in performance. Seems reasonable.
Okay.
But as innovations accumulate and A gets bigger, that same 10% relative increment in A yields a larger relative jump in performance. Why?
Yeah.
Because your baseline performance is already so much higher thanks to all the previous innovation.
So the bang for your buck from new ideas actually increases as the system gets smarter.
Precisely. It's a non-diminishing return, maybe even an accelerating return on intellectual investment. This is completely different from hardware, where adding 10% more transistors almost never gives you a full 10% performance boost anymore due to all sorts of overheads and limits.
So algorithms have this built-in positive feedback loop for improvement.
You could say that. The more algorithmically advanced we become, the more impactful each subsequent advance can potentially be.
Okay, and you mentioned calibrating A using historical examples like the transformer.
Right. We could say, decide that a major paradigm shift like the transformer architecture, which really changed NLP around 2017, represents gain 1. Then we'd look at the performance jump it provided on relevant tasks compared to older methods. Maybe it was roughly a 10x boost on certain benchmarks on the same hardware. If G quotes is 10 and Abel 1, then X bolt 1 is 10. So law would be the natural logarithm of 10, which is about 2.3. The exact number isn't the point, but it gives us a way to put a scale on A and understand the relative impact of different innovations. The key is consistency in showing how improvements compound.
Okay, this makes sense mathematically, but you mentioned a big challenge. In the real world, new algorithms usually run on new hardware. It muddies the water.
Hugely. You see a paper claiming amazing results with a new model, but they ran it on the latest $10,000 GPU with twice the memory of the baseline system. How much of that gain was the algorithm, and how much was just the beefier hardware?
It's like that race car analogy, new driver, new car. Hard to tell what made the difference. So how do we fix that? How do we isolate the algorithmic gain?
This is where the Williams box comes in. It's our proposed solution. A standardized benchmarking protocol designed specifically to ensure fair apples-to-apples comparisons. Think of it like a controlled scientific experiment for AI algorithms. We lock down everything except the algorithm itself.
Okay, what are the rules of the box? You mentioned ISO something.
Right. 3 key ISO constraints. First, ISO compute.
ISO compute, meaning?
Meaning competing algorithms must run with the exact same computational budget, same total number of FLOPs, or same runtime on identical hardware. This stops one algorithm from winning just by crunching more numbers, by using more raw power. It forces a focus on efficiency.
Makes sense. No brute forcing allowed. What's next?
Second, ISO energy. Energy consumption must be kept constant or carefully matched. Both algorithms use the same wattage for the same duration or expend the same total joules.
So no winning by just cranking the power dial way up.
Exactly. An algorithm might seem faster if it's guzzling power, pushing the hardware to unsustainable limits. ISO energy ensures gains are genuinely smarter, not just more power hungry. Plus, it's crucial for thinking about environmental impact.
Good point. Okay, ISO compute, ISO energy. What's the third?
Third is ISO memory. Memory usage and other hardware constraints are held constant. Same RAM footprint, same number of GPUs, same configuration.
So no cheating by loading huge data sets into extra memory that the baseline couldn't access.
Precisely. Or using massive batch sizes that wouldn't be practical in many real-world deployments. ISO memory ensures that comparison reflects realistic operational constraints.
Okay, so the Williams box is like a clean room. ISO compute, ISO energy, ISO memory. The only variable is the algorithm itself.
Exactly. It guarantees that any performance difference we see is genuinely down to thinking smarter, to the algorithmic ingenuity. This rigor is vital for accurately measuring Williams' gain and showing how an algorithm performs as a true drop-in replacement under real-world conditions. That's super relevant for industry adoption, efficiency metrics like accuracy per FLOP or throughput per watt.
And how do we share the results transparently? You mentioned a W card.
Yes, the W card, like a nutritional label for the AI experiment. It's a concise report, similar to a model card, detailing all the fixed conditions: hardware specs, power settings, memory limits, compute budget used, and of course, the outcomes for each algorithm compared. Publishing these W cards allows anyone to replicate the experiment, verify the gains, build trust, and accelerate progress based on solid evidence.
I like that. Transparency and reproducibility. Okay, so this Williams box sounds great in theory. Did you actually test it? Put it into practice?
We absolutely did. To prove Williams' law wasn't just theoretical, we ran an experiment we called Old GPU, New Tricks.
Old GPU, new tricks. I like the sound of that. What was the goal?
The core idea was simple, but challenging. Could algorithmic improvements alone double the performance of a legacy hardware system? No new chips, just smarter code. Could we bring significant new life into old silicon? We wanted to put the law and the Williams box methodology to a real test.
Okay, tell me about the setup. What was the old GPU?
We deliberately chose an NVIDIA GTX 1080 from 2016. It has 8 kilobytes of memory.
Okay.
By today's standards, that's definitely legacy. We effectively froze its architecture and performance in time, ran it on Ubuntu, CT11, consistent drivers for everything, no hardware variables.
And the task.
Image classification on CFAR 10, a standard benchmark. We measured two key things: throughput images per second at a target accuracy and time to train to a fixed accuracy level. Gives you both inference and training efficiency.
Okay, and the baseline algorithm. What was the old trick?
The baseline was designed to mimic a standard setup from 2016 when the GPU was new. A ResNet 18 model trained with basic stochastic gradient descent, SGD, standard data augmentation. Pretty vanilla for that era.
Got it. And then the new tricks. What software magic did you apply?
This is where it got interesting. We threw a suite of modern techniques at it, all purely software. We upgraded the optimizer from SGD to SAM sharpness-aware minimization. We added advanced regularization and augmentation, mix-up, cutout, learning rate warm-up, cosine decay, things not common back then.
Okay.
We swapped the architecture from ResNet 18 to EfficientNet V0, a much more modern, efficient design, but carefully tuned to stay within the exact same 8 GB memory limit. That was crucial.
Right, ISO memory.
Exactly.
Well,
We also used FP16 mixed precision training with the GTX 1080 supported it and enabled optimized KDNN kernels.
so all software level changes. No new hardware. And you ran both setups in the Williams box.
Absolutely. Same GTX 1080,
Yeah.
same batch size, same number of training epochs. Critically, we capped power at 180 W for both runs ISO energy. And we carefully adjusted things so both methods used roughly the same total FLOPs, around 5 quadrillion ISO compute. Memory stayed under 7.5 GB ISO memory. Full Williams box control.
How did you track all that? The power, the FLOPs?
Meticulously. We logged throughput and accuracy constantly. Used NVIDIA SMI to monitor power, ensuring total energy consumed was nearly identical, about 330 kilojoules for both runs, within 5%. We instrumented the code to count FLOPs per batch, verifying ISO compute despite the different architectures. We published a detailed W card with all settings, released the code, full reproducibility.
You even did an ablation study, turning things on and off?
We did, to see which tricks contributed how much and to show that compounding effect.
Okay, the moment of truth. After all that careful setup, what happened? What were the results?
The results were crystal clear. Compelling validation for Williams' law. The improved algorithm, the new tricks, reached 93% accuracy on CIFAR 10 in half the time of the baseline. 0.95 hours versus 1.9 hours.
Half the time, a pure 2x speed up in training.
Exactly. And throughput. The baseline processed around 800 images per second. The improved algorithm, around 1,650 images per second.
Boy, that's more than double.
A 2.06x increase, actually. So that translates directly to a Williams gain G of about 2.006 for throughput.
So on fixed 6-year-old hardware, you got a 2x performance boost just from software.
Just from smarter algorithms. We achieved the benefit of a hypothetical 2x faster GPU, but purely through software, using the exact same energy. The GTX 1080 didn't get faster, the code running on it did.
That's amazing. Was it just faster or better too?
It was actually better too. The new algorithm reached a slightly higher final accuracy, 94.5% versus 93.0%. So it was a Pareto improvement, faster and higher quality. If we fix the target accuracy at 93%, the new method used only about 48% of the compute the baseline needed. Fundamentally more efficient.
So interpreting this with the A index, if the baseline was A0, these tricks gave you a performance multiplier of 2.06.
Right. And if we assumed our lambda was around 0.7, that implies these innovations represented about 801.05 units on our conceptual scale. A significant step up in algorithmic intelligence.
And the ablation study, did one trick do all the work?
No, and that was key. The ablation showed no single silver bullet. EfficientNet gave maybe a 1.4x boost, mixed precision about 1.1x, the software optimizations around 1.2x. Regularization helped indirectly. Crucially, these factors multiplied. 1.4, 1.1, and 1.2 is roughly 1.85. Close to the final 2.06 when you account for interactions. It beautifully showed the compounding effect Williams' law predicts. It was the combination, the stacking of ideas.
So the old GPU new tricks experiment really delivered concrete proof. Even on aging hardware, modern algorithms can smash old performance limits. Williams' law in action.
Absolutely. And it showed the Williams box methodology works for quantifying that progress rigorously.
Okay, so this isn't just a one-off lab experiment. You're saying real-world AI progress constantly backs us up. It's happening everywhere.
It really is. Once you start looking through the lens of Williams' law, separating algorithmic gains from hardware gains, you see it driving progress across the board.
Give us some examples.
Okay, think about image recognition. Between 2012 around AlexNet and 2019, the compute needed to get that same AlexNet level accuracy on ImageNet dropped by a factor of 44.
44 times less compute.
Yes. But over that same period, hardware speed, roughly speaking, only improved by about 11x.
So hardware got 11x faster, but efficiency improved 44x.
Exactly. That means algorithmic innovations alone, things like ResNets, better training, smarter data augmentation, delivered a compounding gain of roughly 4x on top of the hardware improvements. That extra 4x multiplier came purely from algorithms.
Wow. Okay, what else? Recent stuff.
Look at large language models. DeepSeek R1 in 2025 introduced some very clever data augmentation and reward fine-tuning methods. Relatively subtle software changes, but they produced an exponential performance jump on fixed hardware. Classic Williams law.
And the jump from, say, GPT-4 to GPT-4.5, was that mainly hardware?
Not primarily, no. Much of that improvement came from refined attention mechanisms, better alignment techniques, new self-supervised training ideas, all algorithmic innovations. The hardware didn't radically change in that specific step. Accumulated ideas unlocked the new capabilities.
What about areas outside language, like science?
AlphaFold 2, DeepMind's breakthrough in protein folding in 2020. That wasn't just about throwing more GPUs at it. It was fundamentally about innovative neural network architectures and new training strategies designed specifically for that complex biological problem. The algorithm was the key.
Okay, that makes sense. Thinking smarter about the problem itself.
Or consider sparse expert models using mixture of experts, MOE architectures like in switch transformers.
Right, where different parts of the model handle different input.
Exactly. They dramatically increase the effective capacity of the model without needing proportional hardware growth. Each new MOE technique, each smarter routing algorithm, incrementally raises A, giving exponential performance gains with only modest increases in H. Smarter use of existing hardware, multiplying the output.
And you mentioned prompting earlier, chain of thought and chain of draft.
Yes, perfect examples. Chain of thought, COUT, was a pure algorithmic shift, a prompting strategy. It instructed models to show their work, generate intermediate steps. Instantly, models could solve reasoning problems they failed at before. That was a jump in A, boosting performance dramatically on certain tasks.
And chain of draft built on that.
It did. COD took COD and made it vastly more efficient. It slashed the compute needed the number of tokens processed by about 13 times while keeping the accuracy.
A 13x Williams gain just from a better prompting method.
Exactly. Imagine trying to get a 13x speed up from hardware alone. That would take multiple GPU generations, maybe a decade. Or you'd need 13 times the hardware, 13 times the cost, 13 times the energy. COD did it overnight with a smarter method.
And it shows the compounding, right? COD added to COD, didn't replace it.
Precisely. It made an existing capability vastly more efficient. This stacking of ideas is the heart of Williams' law.
Okay, so the evidence seems pretty compelling. What are the broader implications then? If algorithms are such a powerful driver, how should that change things? Let's start with industry, R&D investment.
Well, if you're a company building or using AI, Williams's law strongly suggests you should be investing heavily in algorithmic innovation, not just chasing the latest hardware treadmill. Why spend millions on a hardware upgrade for maybe a 2x capacity boost when a fraction of that spent on an R&D team might improve your model efficiency by 2x, 3x, maybe more?
Achieving the same outcome with less capital, plus you get proprietary algorithms.
Exactly. The ROI on algorithmic R&D can be extremely high. Companies should really start tracking their internal A index, their algorithmic efficiency metrics, just as closely as they track their FLOPs or hardware spend.
What about product cycles? And older hardware? Our old GPU experiment seems relevant here.
Absolutely. It shows legacy hardware isn't necessarily obsolete. Better software can give it a massive new lease on life. This means companies can extend the useful life of deployed hardware servers, edge devices, whatever, saving huge costs and reducing e-waste simply by deploying software updates with algorithmic improvements.
It's like getting a free hardware upgrade through software. That has big economic and environmental benefits.
Immense benefits. Postponing costly hardware refresh cycles while still improving performance is a huge win-win.
Okay, what about policymakers, economists trying to forecast AI's impact?
They really need to factor this in. Many forecasts still seem tied to hardware trends, which are somewhat predictable. But Williams' law means AI capabilities can leap ahead unpredictably due to algorithmic breakthroughs, even if hardware progress slows.
So assuming steady hardware-limited growth could be dangerously wrong.
It could. And it means compute power alone isn't a sufficient metric for AI capability or national competitiveness anymore. A nation with less compute but more algorithmic ingenuity could potentially leapfrog others.
So policy might need to incentivize algorithmic R&D, not just chip manufacturing.
Potentially, yes. And certainly for environmental policy, algorithmic efficiency is key. It helps decouple AI growth from its energy footprint, which is critical for sustainability, doing more AI with less power.
How should this change things for the research community? What should scientists focus on?
It really reinforces the value of certain research areas: efficient architectures, better optimization methods, knowledge distillation, data-centric AI, model compression. These aren't just engineering details anymore. They are the core engine of progress.
So less focus on just chasing state-of-the-art accuracy at any computational cost.
Ideally, yes.
Right.
Grants and conferences should place more emphasis on algorithmic efficiency. Reward work that achieves great results with less compute. That encourages innovation in the right direction.
And it might encourage looking beyond standard deep learning, maybe drawing inspiration from neuroscience or other fields.
Absolutely. It opens the door to exploring fundamentally different, potentially much more efficient ways of processing information. Interdisciplinary work becomes even more valuable.
You also mentioned standardizing benchmarks, using the Williams box and W cards more widely.
Yes, we strongly advocate for that.
Yeah.
Just like energy efficiency benchmarks, like Energy Star, became standard for hardware, performance per compute or performance per energy benchmarks should be standard practice in AI R&D. Things like MLPerf or DonBench are already moving in this direction. Standardizing on Williams box principles would make it much easier to track genuine algorithmic progress over time.
Okay, finally, what about the ethical or social side? This acceleration via algorithms, is it all good?
It's definitely a double-edged sword. On the plus side, it can democratize AI. Smaller teams or companies with less hardware can still compete and innovate if they have clever algorithms, and the environmental benefits are clear.
But the downside?
Rapid progress, especially unpredictable leaps from algorithms, can outpace our ability to understand and manage the societal consequences. Policymakers need to watch for algorithmic shifts, not just hardware cycles. There's also the question of who benefits. If these efficiency gains are widely shared through open research, great. If they become closely guarded secrets that concentrate power, that raises concerns.
So an ethos of openness in algorithmic efficiency research is important.
Very important, we believe. Similar to how basic hardware improvements eventually benefit everyone, sharing fundamental algorithmic efficiency techniques helps ensure the progress is broadly beneficial.
Okay, this has been incredibly insightful. Let's try to wrap up. What are the key takeaways here?
I think Williams' law offers two things: a description and a prescription. Descriptively, it explains a huge part of AI's past success. It wasn't just bigger machines, it was fundamentally better ideas. Ingenuity drove many breakthroughs. Prescriptively, it charts the path forward. To get the next big leaps in AI, the most strategic focus, the best investment, is likely in better algorithms, not solely more machines. That's the paradigm shift.
So what does this all mean for you listening right now? It means you're living in an era where software ingenuity, pure creativity, and algorithms is the true engine of AI progress. It's compounding, it's accelerating. We are definitely not nearing the end of AI advances because of hardware limits. The frontier has just moved. It's shifted to the algorithms, to the code, to the ideas. It really challenges all of us to think smarter in every sense, recognizing that these seemingly small, continuous improvements in algorithms can stack up to have massive transformative effects long term. It really is a call to innovation.
And it leaves us with a really provocative thought, doesn't it? If algorithmic innovation can already multiply performance by factors of 2, 4, even 13 on existing hardware, what new capabilities, things that seem impossible today, will be unlocked by the next wave of intellectual ingenuity? How will this fundamental shift in what drives AI progress reshape our world in ways we can probably barely even imagine right now?